Hello everyone and welcome to class. This is our first video of the semester and our just get it started here. So our objective is to understand number systems with different bases, and the reason is so we can understand the base system that we typically use, and that's base 10. When I'm in class physically, not online, I usually start off with these birthday cards hanging up on the wall. Now, these birthday cards are available in your week 1 resources, so you can print them out yourself and try them out with your friends or in your own classroom. It works a little bit better when I have a live class I can go through with and ask people about their birthdays, but I can kind of explain what would happen if we were in a classroom with this, and you can kind of follow along. So the first thing I do is say, look at these birthday cards and find out which cards have your birthday on it. So the day out of the month. So for instance, mine is May 4th, and I only see one card with a 4 on it, and it's this card right here. Now, that's not very interesting. Other people have more interesting birthdays with more cards with their birthday on it. So let's suppose I asked a student randomly out of the classroom, tell me which cards have your birthday on it, but don't tell me your birthday. And they picked this card, this one, and this one. Could you tell me what their birthday was? Now, you could look and say, well, there's out of these cards, 26 is the only number that shows up on all of these cards and none of the rest. Notice these two cards, this one and this one, don't have a 26 on it, so obviously their birthday is a 26, or the 26th of whatever month it is. I normally give them their birthday pretty quickly without having to search through the cards and trying to figure it out. So there's a trick to it. Let's look at another birthday. Let's suppose I picked this card, this one, and this one. Could you quickly tell me what birthday it is? Well, if you couldn't figure it out without pausing it, hopefully you would see that it's the 30th. And so I usually do this for a few students. Sometimes it gets it wrong, but it's only because the student didn't see that, hey, this card had the 30th on it, and they only told me 3 of them. But if they tell me, which cards have their birthdays on it, I can quickly tell them their birthday. And it all has to deal with this top left number right here. So going back to our example with the 26. Here's the 26, there's the 26, and there's the 26. See if you can pause the video and see how I use these top numbers up here, just the top left corner number, to figure out it's the 26. Or if we're looking at the 30th, cards with the 30th are right here, 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 and here. How would I use those top left corners to figure out their birthday is the 30th? And so if you like I said, in class I can ask you more questions and kind of lead your thinking, but here I'm just going to go ahead and tell you how I do both of these. So for the 26, if you couldn't see it before, using this one, and this one, these are the only 3 cards with the 26. Notice I'm going to add those 3 numbers up, and that gives me 26. For the 30th, I'm going to use this card, this one, and this one. And notice those 4 numbers add up to 30. Take a moment and try it with your own birthday and see if it adds up for you. Now for me, my birthday is the 4th of the month. And so that doesn't really give me much interesting things. It's just one card that has a 4 on it. It's this one, and it's in the top left corner. So if somebody picked just this middle card, I know their birthday's on the 4th also. What if their birthday was on the 7th? Which cards would they show me? Well, they would show me this one, and this one. These two don't have a 7 on it, so that would tell me to add up 4 plus 2 plus 1. And that would say, hey, your birthday's on the 7th. What if their birthday was on the 31st? Which cards would they pick for the 31st? Well, it looks like that one's got a 31, 31, 31, 31, 31. So you'd add up 1 plus 2 plus 4 plus 8 plus 16. And that adds up to 31. So this is a fun little trick to show your family. You know, they can pick the cards. I showed it to my 4-year-old once. Actually, he's 5-year-old, and he just said, well, you probably just have them memorize which ones are on which card, which, like I said, you could do, but, you know, you'd have to have a pretty good memory to come up with it that fast. I like looking at it and saying, hey, you know, what we're using here is a mathematical trick. And so how do we get these numbers on these cards? That's what we're going to look at today. And it all goes back to, in this case, a base 2 number system, or binary, which you may have heard of when you hear people talk about computers and coding and things like that, because they use the binary system quite a bit. So in order to understand binary, let's look at our base 10 number system that we're so familiar with. So for instance, let's suppose we have the number 3,518. When we take a number like that, what we're really saying is we have 8 ones, 1 10, 5 100s, 5 hundreds, and 3 1000s. And so this is what our base 10 number system looks like. You could also do it like this. Let's suppose for each place value here, we have a 10 raised to a power. That's why we call it base 10. And so the ones digit is 10 to the 0, because remember, anything raised to the 0 power is 1. The tens digit is 10 raised to the first, because 10 to the first is 10. The hundredths place value here is 10 raised to the 2. 10 squared is 100. And then the thousands is 10 cubed here. And we could keep going if we went to 10,000s or 100,000s or so forth. It'd go 10 to the 4th, 10 to the 5th, and so on. And so what I'm really saying here is 8 times 10 to the 0. And then 1 times 10 to the first. And then 5 times 10 squared. And then 3 times 10 cubed. Let me write that out. Expanded form here. So I'm saying basically it's like 3 times 10 to the third plus 5 times 10 squared plus 1 times 10 to the first plus 8 times 10 to the 0. That's what I'm really adding up here. That's 3,518. And so this is like 3 times 1,000 plus 5 times 100 plus 1 times 10 plus 8 times 1. And when you add those up, you get 3,518. Now this is base 10. So all we do to figure out base 10 is we say 10 to the 0, 10 to the first, 10 squared, 10 cubed. Underline there is your base. So when we talk about binary, we're dealing with ones and zeros. So let's say you have the number 1, 0, 1, 1, 1. We'll do it like that. And we're saying that this is in base 2. So a lot of times we'll write a subscript 2 to say that the base is 2 and it's not like base 10 like we already know. So if that is base 2, how do we write it into our normal base 10 number system? So just like we did with the last one where we had 10 raised to a power, we're going to do the same thing, take our base and let 2 be raised to that power. So this place value right here is like 2 raised to the 0. This is 2 raised to the 1, 2 squared, 2 cubed, and 2 to the 4th. So when I look at this, this is like saying 1 times 2 to the 0. 1 times 2 to the 0 plus 1 times 2 to the first. And my hand's making all these marks down here. Sorry about that. Plus 1 times 2 to the second. 1 times 2, oh, not 1, 0 times 2 to the third, and then 1 times 2 to the fourth. So it's like I'm adding all these up. Now you do enough binary, you start to memorize your powers of 2 here. 2 to the 0 is 1, so it's like saying 1 times 1. 2 to the first is just 2. 2 squared is 4. 2 cubed is 8. And 2 to the fourth is 16. And so 1 times 1 is 1, 2, 4, 0, and 16. I'm just multiplying these straight across and adding these up. 1 plus 2 is 3, plus 4 is 7. 7 plus 16 is 23. So this number right here in base 2 is the same thing as 23 in our base 10 number system. So I might ask you to say, hey, here's a number in binary, convert it to decimal or base 10, and that's how you would do that. So a couple of things to keep in mind before we try out a few examples here. In our base 10 number system, what digits do we have? So we say we've got the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So there are 10 digits. We got 10 of those in base 10. What about base 2? So in base 2, notice we only have 2 numbers, 0 and 1. We never reach the 2. Just like in here, we never actually reach 10. Like we reach 10, and if we have a tens place and a ones place, but we never have the actual number 10 written in here. Here we only have 2. Later on, we'll talk about like base 3 and base 5 number systems. You can go to any base you want. You can go to base 16. That's used a lot in computers also. But these are the main ones we'll focus on. Base 3 only has numbers 0, 1, and 2. 3 numbers, but only 0, 1, and 2 are listed. We don't hit a 3. That's when we carry over a number. Base 5, how many do you think base 5 has? Try listing them out. So base 5 has 0, 1, 2, 3, and 4, but no number 5 there. So that's just some things to keep in mind. You'll see that on your homework and your quiz, like to list how many numbers are in each of those bases. So try another one. Let's try to convert from binary to decimal, and let's do number 1011. Convert that into decimal. So pause the video and try converting that. Now, if you're just learning this or you're struggling with it, it might help you to just write these out like this. And then I always tell my students to write out these up above. 2 to the 0, 2 to the first, 2 squared, 2 cubed. If we had more numbers here, we go 2 to the fourth, 2 to the fifth, 2 to the sixth, and so on. And then down below, we can say, okay, this is 1 times 2 to the 0, or 1 times 1, plus 1 times 2 to the first, plus 0 times 2 to the second, or 4, plus 1 times 2 cubed, which is 8. So these went right here, like this. And then I've got my normal number 1011. That's where those come from. So multiply these out. 1 times 8 is 8, plus 0, plus 2, plus 1. And so adding that up, I get 11. So it's 11 in decimal, or base 10. The next thing I want you to do is I want you to count to 30. Let's go to 31 using binary. So make you a list on your paper. Go. This is in base 10. 1, 2, 3, 4, 5, all the way up to 31. So here we go. I've got my numbers listed out to 31 here. Yours can probably fit I don't know, in 2 columns. It doesn't really matter how many columns you have, as long as you've got room to write your binary numbers next to it. But this is counting in base 10 all the way to 31. Notice once we hit 9, there is no 10 to write, so we start over at 0 and then add 1 into our tens digit. Then we go 1 through 9 again, and then we add another 1 to the tens digit to get 2 tens plus 0 ones. In fact, when my kids learn this, I make them to say like a number like 26 as 2, 10, 6, 1. That way they start to learn that, hey, I mean, we've got 2 tens here and 6 ones that are being added up, not just 26. But that's how our base 10 number system works. So now I want to do the same thing, but do it in binary. Count to 31 in binary. So as I write this out, we start with 1, and then 2 looks like this, 1, 0. 3 would become 1, 1. Now with 4, notice if I add a 1 right here, it becomes 0. Carry the 1, add a 1 right there, that becomes 0, and then you get 1. Now if that confuses you, go back and go to what we did on the previous slide right here where we convert numbers. How is 100 equal to 4? Remember, we're going to say 0 times 2 to the 0, 0 times 2 to the first, and then 1 times 2 squared. 1 times 2 squared is just 4. And then we're going to add another 1, so this becomes 101. Adding another 1, you get 110. And then we get 111. And then 1000. And that's our 8. I know that this may be fast for some people, so just to kind of explain that again, at 8, how is 100 in binary the same thing as 8 and decimal? Remember, this is 2 to the 0. Whoops, not 20. 2 to the 0. This is 2 to the first, or 0 times 2 to the 0 plus 0 times 2 to the first, 0 times 2 squared, plus 1 times 2 cubed. And that's where you get 8. 1 times 2 cubed. 2 cubed times 1, that's like saying 8 times 1, which is 8. Now I know some students might want to say, well, how come we can't just say, let's go back to that other page. How come this doesn't have a 2 in it or a 3? And remember, with binary, we're only dealing with ones and zeros. So I want you to complete this chart out. Pause the video, see if you can complete it on your own, then I'll post the answer. Alright, so here's what I've got for my result. You can check it with yours. Now, if you're having difficulty with this, I would suggest you go to the resources and download the dot cards that I have for you. And usually what I have students do in my class as they count these out is to use these dot cards. Now I don't have physical cards I can show you on the computer, but I think you can follow along with what I've got here. I've got 5 cards, and this one on the right has 1 dot, 2, 4, 8, and 16. Now these green, whoops, not that green, these greenish teal cards, that's going to represent the back of the card. So what I mean by that is when I move this over, just pretend like I flipped over the card. And so the card's face down, and that's the back of the card. And so if I've got something like this, then this card, and this card are all flipped over, and these are facing up. And I just don't, I mean, I guess I could stack these up right here so you don't get confused by it. And so we can count from there. Let's see, let's move these over. Oh, stay with you. And so for instance, let's suppose we wanted to count, and I just want, we'll do the first, I don't know, 5 numbers here. 1, 2, 3, 4, 5. And I want to count in binary. This is in decimal here on the left, but I want to convert these to binary. So I'm going to use these cards to help me. So I'm going to lay them out, and I'm going to flip them all over. So they're all flipped over, and when they're all flipped over, that represents basically the number 0. But then when I count in binary, I'm going to say, okay, where's my number 1 here? So I flip it over, and this represents, when we see it like this, it's going to represent the number 0, 0, 0, 0, 1. So number 1 is the same thing as that. Now on the other page we had it written out like this, and that's fine. Typically when we write numbers, like if I'm writing number, I don't know, 324 in binary, I don't put zeros in front of it because they have no meaning. But as we're counting out, because we're making these 5-digit numbers for this practice, we can do that. So when I add 1 to this, I'm actually, remember, you can only have 1 and 0, so I can't write this as number 2. It becomes a 0 again. And then this card gets turned on. And so notice we have, this becomes a 1 and that becomes the 0. So anytime the card's flipped over, that's being represented by the number 0. And so this becomes 0, 0, 0, 1, 0. And notice I've got 2 dots. That's our, the sum of the cards that are face up, the dots on them. That's going to represent our decimal equivalent. So when I get to the number 3, I'm going to flip this card over. Oops, this thing keeps separating on me. I group them and then they separate. Here. I flip this card over and now this becomes a 1 up here. And so I count these 2 cards, or these dots here, 1, 2, 3. So this is the number 0, 0, 0, 1, 1. And then when I get to the number 4, let's move this down a little bit. So I'm going to add 1 to this. So I'm going to flip that card. That gets flipped. I flip this card. And then this card gets unflipped. So it's going to look like that. So this becomes a 1. And then these become zeros. So this becomes 0, 0, 1, 0, 0. Notice there are 4 dots total. When I get to 5, I'm going to add a 1 to this column right here. So this card gets flipped again. And we're just going to add the 1 right there. So it becomes 1, 0, oh, not 1, 0, whoops. 0, 0, 1, 0, 1. Notice we have 4 dots right here plus 1 dot right there equals our 5. So when we get to 6, the number 6 in binary, we'll do 7, 8, and 9 here also. We'll just do 6, 7, 8. And my computer keeps freezing in certain sections like that, so ignore that word that says group there. So when I get to 6, I'm going to flip this card, which is going to send this card right here on top of it. This card gets unflipped. And so it starts to look like this. That card's on, this card's off, that card's on. I switch colors. There we go. And so it becomes 0, 0, 1, 1, 0. And notice the total number of dots here. There are 6, which is our decimal equivalent. When I go to 7, this card gets flipped, so it gets taken off. And so there's no need to carry any numbers over. You just count this card right here. Some people say this one gets turned on, these 2 are off, is what they say. Notice the total number of dots is 7, so it's 0, 0, 1, 1, 1. When you get to 8, you're going to flip this card. Flipping this card means you're going to carry the 1 to this one. It's already turned on, so it gets turned off. Which carries the 1 to this one, so that one's already on, so it gets turned off. And then that one stays on. So it looks like this. 0, 1, 0, 0, 0. Now you should keep being able to do this. This is enough digits right here to go all the way up to 31. So if this helps you, you can. Notice there are 8 dots on this one to give us the 8 and decimal. How would you do 9? Well, 9 you'd start by flipping this one over. and that would become, the number 9 would be the same thing as 0, 1, 0, 0, 1. 8 dots right here, 1 dot right there, they add up to 9. So if you can, you go back and check this chart. I kind of did this one out quickly. You can double check, let me know if you see anything there that looks funny, but it all worked out in the end. So that 31, notice that they're all on. So you count them all. So if we look at something like our cards here, would we get 31 by adding all these up? Let's move all these footballies over, all this mess out of the way. Well, let's count them. So 31 looks like 1, 1, 1, 1, 1. There are 16 dots here, 8 here, 4 here, 2, and 1. And when you add up all these numbers, you get 31. So if that looks familiar to you, it should. If you go back to the beginning of the lesson, we had our base 10 number system, or our birthday cards right here. And remember, these numbers added up to 31. So now I want you to pause the video, take a look at these birthday cards, and see how you figure, can you figure out how these work and how they relate to binary numbers. All right, so if you're looking at this, let's look at our number. Let's go to, I don't know, 26 again. That's what we started with. So 26 is here, here. There's one other spot. Where was it? Right here. And we said we added up the numbers 2, 8, and 16, and you get 26. So look at your chart that you made counting in binary. Where is 26 base 10 is equivalent to what in binary? Well, it is 1, 1, 0, 1, 0. And so you got 1 times 16 plus 1 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. And so anytime that you've got a number, say your birthday was on the 26th, then it's only, the only cards that it's listed on are the ones that would be having a 1 in that digits place in binary. So let's say your birthday is on the 20th. So if your birthday is on the 20th, let's erase all this mess, then you're going to be here, here, and that's it. This is going to be 1, 0, 1, 0, 0. That's the binary number for 20. Once again, if we were looking at the binary number for 20 using our dot cards, notice let's see here, check 20, 1, 0, 1, 0, 0. But if we're looking at our dot cards here, this is what it would look like. This would be covered. So would these two. And so notice our dots here, number of dots. We got 16 dots here, 4 dots here. That up to 20. That's really nothing different than looking at your birthday cards with, instead of dots, you have the number listed in the top corner. So for the number 20, notice these are this is basically saying 16 dots and 4 dots. And all the numbers on this card have a 1 in that spot when you're listed out in binary. All the numbers on this card have a 1 in that spot. So 20 is the only number with 1s in that spot and 0s everywhere else. And then 21 is going to have a 1 in this spot also, because you're going to add that 1 to it. 22 would have a 0 here and a 1 in that spot, because you're going to add 2 to 20, and so forth. So check that out. Rewatch the video if you need to. If you have questions, let me know. That's the basics to how the binary number system works, and how to convert from binary to decimal. Now, one more thing I want to show you today is how to convert from decimal to binary, because if you can go back and forth, that's, will help you understand both number systems a little bit better. So let's take a look at a number in decimal. Let's say we got 254, and we want to convert that to binary. Now, looking up online, there's several different ways you can do this. I'm going to show you the way I find that is easiest, And if you want to do it a different way, that's fine by me, but I think this way is the quickest and most easy for the majority of my students to understand. So the first thing I do with this is I start listing out, I know I want to convert it from base 10 to base 2. So I've got base 2 here. I'm going to write out 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, and then the equivalent of to what these things are right here. 2 to the 0 is 1, 2, 4, 8, 16. Now, if I subtracted 16 from the number 254, I'd get a number bigger than 16. So I'm going to keep going as high as I can. So I got 2 to the 5th. That's the same thing as 32. I'm just doubling the one before it. I got 2 to the 6th. That's 64. 2 to the 7th. That's 128. And now that looks like I'm getting into some numbers that are going to, my next number would be what? 256. That's 2 to the 8th is 256, which is a number bigger than 254. So I'm going to stop there. And so the first thing you do is this largest number right here is subtract it from 254. And what do you get? It should be 126. And so I subtracted 128 from it. So I'm going to put a 1 underneath that. I subtracted that from it. Next thing I'm going to do is subtract 64 from this number. So subtract 64. And I get 62. I subtracted 164 from it, so I put a 1 underneath that. Next, subtract 32. And I get a 30. I subtracted 132, put a 1 there. Next, I'm going to subtract 16. And I get a 14. I subtracted 116, I put that there. I'm just going to write 14 right here. Next, I'm going to subtract an 8 from it. When I subtract 8, I get a 6. I subtracted 1 8. I'm going to write that right there. Next, I'm going to subtract a 4. Subtracting a 4, I get a 2. I subtracted 1 4, put a 1 there. So I'm left over with 2. Next, I'm going to subtract a 2. And when I subtract a 2, I get 0 left over. So I subtracted a 2, and then I get 0 right here. So this number right here is the same thing as 254 in binary. Now, you're going to wonder, like, do I always get a bunch of 1s in a row? So let's look at another example to show that's not always the case. We just did 20 a few minutes ago, and we found out what 20 was in binary by counting. But let's suppose we have 20 in decimal, and we want to convert to binary without having to count up to 20. Let's do the same method. So I'm going to say 2 to the 0, 2 to the first, squared, cubed, to the fourth. 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 8, 16. If I go any further, I'm going to get a number bigger than 20, so I'm going to stop there. So the first thing we do is take the biggest number and subtract it from the number I'm wanting to convert. So 20 minus 16 is 4. So I subtracted 116, I'm going to put a 1 there. I can't subtract 8 from 4 because 8 is larger. So I'm going to put a 0 there. I can subtract a 4 though. So subtract a 4, and I'm left over with 0. So I subtracted 1 4. I have nothing else to subtract because I'm down to 0, so this becomes 0 0. So this number is the same thing as 20. 20 decimal is the same thing as 10100 in binary. Let's try one more. I'll pause it and let you try it out. Let's try 17. So without looking at where you wrote them out earlier, do it this method, convert from decimal to binary. All right, so you should have paused the video, given it a try. Let's write these out to the 0 and so forth. Once you get past 16, you're at a number bigger than 17, so no reason to do 2 to the 4th. Take that biggest number, 16, and subtract it from 17. And you get, so we subtracted 1/16. We're left over with 1. You can't subtract 4 from 1. You can't subtract 2 from 1. You can subtract a 1 from it. So if I subtract 1 from it, I get 0 there. So I subtracted 1, 1. So 1, 0, 0, 1 is the equivalent to 17 in decimal when you write it in binary. Okay? So we talked about how to count in binary, how to convert from decimal to binary, and how to convert from binary to decimal. That's what your homework is going to be on tonight. Let me know if you have any questions. I'll provide these resources that we used in the video, and if you need some extra help, like I said, just let me know. Thanks for watching, and I hope you have a great first day.